All right. So this is chapter 2.1. We're going to be focusing on a lot of things about angles that are going to be fundamental for us in trigonometry. We're going to learn to draw angles in standard position, convert between degrees and radians, find coterminal angles, and to find a reference angle. These other things we're going to focus on in the next half here. All right. Okay, so first off, important object that we're going to use quite a bit is a ray. A lot of our angles are going to be drawn using rays. So some notation with rays, it's really important when you're naming a ray that you start with the end point of the ray and then another point that's on the ray. So you don't want to name this ray FE. That would not be good, because that would imply that we are starting at point F, passing through E, and then continuing forever. So obviously these two things are not the same as one another. So we want to make sure that we start with our endpoint and then the next point that we pass through when we're naming them. A lot of our angles are going to be formed by rays, and angles aren't always formed by rays. Just take, for instance, if we have a triangle, we don't really think about these parts as being rays, but the angle itself can be, right? So if we just thought about this angle here, we could construct that angle using some rays, and it wouldn't really change anything about the angle itself to think about it in terms of rays. Some notation with angles here. So here we have angle DEF. We could also call this angle FED. Either one of those two would be appropriate. One way I like to think about angles is if you just kind of follow the angle itself and draw it, you're going to be touching the appropriate letters in the right order for the name. So if we go D, then to E, and then to F, right? That's creating angle DEF, or the other way, angle F, so point F, down to E, up to D, FED. We could also reference this particular angle as just calling it angle E. That would be another way to do it. In this case, there is only one angle here, but this is going to be less common. In general, we're going to be using those other two options there. The thing to keep in mind when naming an angle like this is the vertex, the point that is the vertex here, has to be the middle letter. So some other ways that we name angles, a lot of times we will draw something in here in the little corner of the angle to indicate its name. So in this case, we could call this angle theta. This is the Greek letter theta. And a lot of times with trigonometry, we're going to use Greek letters to name the angles. Theta is kind of like the default a lot of times, but you'll also see alpha, beta, gamma. Those are going to be used quite a bit. For instance, if we have like a whole triangle here, it might be common to do something like this is triangle ABC, to call this alpha, beta, and gamma here. Just as a way to do it, to talk about the angles versus the sides using lowercase letters. Just to distinguish angles being named using Greek letters just kind of helps you know what we're talking about when we reference something as a Greek letter. Just what we do, nothing super special. Definitely no theta, though. That's one we're going to be using a fair amount. So in trigonometry, a lot of times it's going to be really useful for us to think about an angle as a rotation. So we could think about it as having two rays that start lined up one on top of the other. But then one of the rays is sort of rotated, kind of like the hand of a clock or something, is rotating. And that amount of rotation right in here, that is our angle. How many degrees or how many units of rotation is that? Right? That's what we call the measurement of the angle. Where the angle starts, we refer to that as the initial side, and where it ends, where that rotation ends, we call that the terminal side. And like I said before, the measure of the angle is the amount of rotation that happens between the initial side to the terminal side. Now, the most familiar unit that we probably have for that is degrees. Now, Degrees are not perfect. They're kind of whatever. 1 degree, as we know, is 1/360th of a full circular rotation. So a full circle encompasses 360 degrees. It's kind of an arbitrary number, right? It's something that we've all agreed upon, and it works, and we use degrees all the time, but there are other ways that we can measure angles. And in this class, we're going to learn some other ways that we actually measure rotations or angles. But we will also use degrees a lot, so that's fine. All right, so standard position. So standard position is a really important thing for trigonometry. Standard position is when we draw an angle in the same place on an XY axis. We put the vertex at the origin. We line up the initial side with the positive x-axis, right? So this is the positive side of our x-axis. Then we rotate the terminal side around the origin. So around the origin, whatever the measurement of the angle is, right? Whatever this here represents our measurement, the measurement of our angle. And our terminal side is drawn in the appropriate quadrant, right? We do want to make sure we know the names of the quadrants, right? This is our first quadrant, our second quadrant, our third quadrant, and our fourth quadrant. And we do that, we name it that way because of this trigonometry, the way that we use it to do trigonometry. 1, 2, 3, 4. That's kind of the way, the order of rotation going through the different quadrants. Now, a couple things here. The angle can rotate both counterclockwise like this. Counterclockwise is for positive angles. So unless we're told otherwise, we're going to assume that we're dealing with a positive angle measurement, and we show that with a counterclockwise rotation to the left. And negative angles would be a clockwise rotation. Now, if we were to estimate this angle, this is obviously the y-axis here would be 90 degrees, and this looks like halfway between 90 and 180. So we could call this 135 degrees, this angle here. If we wanted to show negative 135 degrees, we would rotate from the same position, from the same initial side, or rotate clockwise. So in this case, negative 135 would be somewhere down here. And we would show it with the proper rotation. This would be negative 135. These are different angles, and they're going to have slightly different properties that are associated with them. Now, the reason we draw angles in standard position is so that we could compare different angles to each other and use a standard set of properties to figure out different characteristics of those angles. So we're going to be doing this a fair amount. So here are some angles. We have a 90-degree angle. Pretty straightforward. It's right on the y-axis there, 90 degrees. Our initial side, terminal side, vertex on the origin. In geometry, generally, we kept all of our angles in between 0 degrees and 180 degrees, right? We didn't really deal with angles greater than here, which would be 180, right? In trig, we may want to have angles greater than 90 degrees. So for example, here is a picture of a 360-degree angle. Notice the initial side and the terminal side are lined up exactly on top of each other, because a 360-degree rotation is a full circle. We start there, we rotate 360, and we end up in the same spot. We can have degrees that are angles of rotation that are anything we want. You may be familiar with, like, let's say Tony Hawk, right? He's famous for doing a skateboard trick called the 900. It's 2.5 rotations. So because 360 or 900 is really 360 plus 360 plus 180. When you add those all together, you get 900. So we could show a 900-degree rotation similar to the way we showed this 360. We have to show the rotation though. So 900 is one full rotation, another full rotation, and then a half rotation. So a 900 would end right there. 900-degree angle would have an initial side over here, and then a terminal side going right out there. So a 900-degree angle, or degree rotation, is also the same thing as what? This is right here. This is only 180. We have a special name for this kind of relationship here, but when we have something like this, we do actually want to show how many rotations we're having there. Anyway, that's just a quick example of we're going to be dealing with lots of different types of angles, and we need to know how to handle them all. Okay. Then we have some special angles called the quadrantal angles. So anytime we have an angle where the terminal side ends up on an axis, on the y-axis, on the x-axis, on the y-axis down, or on the x-axis, those are called quadrantal angles. And they represent kind of quarter turns. All right, so we have our 0-degree angle is a quadrantal angle, 90 degrees. Right there ends up on the positive y-axis. 180 ends up over here on the negative y-axis. 270, and then obviously again, 360 would be another one. Same thing as 0 degrees. They just have a special name, quadrantal angles. Let us sketch a 30-degree angle. So first off, before we do that, let's just kind of mark some things out that we know. This is our 0-degree spot. Or if we do a full rotation, it's also 360, right? If we rotate all the way up here, this is 90. All the way over here, this would be 180. Obviously, I'm talking about positive angles here, but we're not dealing with a negative, so that doesn't really matter. So a 30-degree angle, my fault. I actually did skip the negative example here, so let's do this. 30-degree, okay. A 30-degree angle. 30 degrees is actually a third of the way to 90, right? 30 over 90 is 1/3. So we need to kind of break this up into thirds. If we kind of break this up into thirds, if these are 3 kind of even pieces here, a 30-degree angle would be 1/3 of the way. So we would have our initial side and our terminal side there. And we want to show the direction of rotation, 30 degrees. There we go. Next, we want to show a negative 135. So this is I'm gonna do this a little bit differently. So this is 0. If I'm going negative, remember I'm going counterclockwise. So I'm gonna go this way. So this would be negative 90, negative 180, negative 270. I don't really need to go, but I guess this would also be negative 360. Okay, negative 135. So 135 is between here, and 135 is exactly 45 degrees off of 90. So 45 degrees is half of 90. So it's going to be right in there. Should have used my ray tool, but that's okay. So negative 135 degrees. I'm using a lot of things that I already know, but right in here is a 45-degree angle. And then this right here is a 90. And those together add up to my 135, right? That's how I'm getting there. This is our initial side. This is our terminal side. I'm going to keep moving forward. You try it. So take a second here, see if you can sketch a 240-degree angle. A lot of different ways we can do it. You see what you got. Go ahead and pause it, and I'm going to do it here. Initial side. So here's our initial side. We're rotating positive, so we're going to rotate this way, counterclockwise. 240. I either want to think about this in terms of its relation to 180 or relation to 270. So I'm going to think about it in terms of relation to 180. So I know that it is 60 degrees more than 180. So I want to go 60 degrees past it. Or I can think about it here. It's 30 degrees less than 270. So it's going to be closer to 270. It's going to be 30 degrees away here, or 60 degrees away from here. And I want to estimate that. I want to try to do it as accurately as I can. But here is our angle of rotation of 240 degrees, starting at our initial side and ending at our terminal side. Okay. All right. Here's the big new thing. So radians. Radians are going to be something we use a lot in this class. So understanding what they are is sort of important. We're going to focus more on how to use them, but I'm going to start by trying to explain what they are. So again, radian is just another unit of measurement for angles. It has to do, instead of thinking about angles in terms of the amount of rotation, we actually think about it in terms of an arc length. So when we have a circle like this, if we want to look at an angle, so let me draw a little line in here. If we want to think about this angle right here, this we call a central angle. The measurement of this angle is considered to be 1 radian, because the arc length that is created, this right here, is equal to the radius. It's that simple. The radius of the circle is equal to the arc length, therefore the measurement of this is 1 radian. Now, the great thing about this is this works no matter how big or small the circle is. 1 radian is going to create the same angle no matter how big or how small the circle is. This has to do with our formula, right? When we think about the circumference formula for a circle, so the circumference of a circle is always equal to 2 pi times the radius length. 2 pi is a constant, so 6.28 something, whatever, you know. When we multiply that by the radius, that's going to give us the circumference of the circle, how big around our circle is. Well, what that really means is that every circle is going to have around 6.28 radiuses all the way around it. And you can see that here, right? If I go from here, this is 1 radius, 2 radiuses, 3 radiuses, 4 radiuses, 5 radiuses, 6 radiuses, and then this little piece, which is that 0.28, blah, 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 right? And also half a circle, right? You can see here, half a circle right here is a little bit more than 3, about 0.14 ... more than 3, right? Because half a circle has, half of this has pi radiuses around it. Anyway, because no matter the size of the circle, there will always be 6.28 or exactly 2 pi radiuses around it. Doesn't matter how big the circle is, the angles that get created will be the same. So we think about the radians as the amount of radii that are in a given circular arc created by an angle. And again, it doesn't really matter how big that circle is or how small that circle is, it's always going to be the same. In trigonometry, we think about the circles as always being what's called the unit circle, a circle with a radius of 1. We'll get more into that in the future, but for us, most of the time, we're just going to assume a radius of 1 because that sort of simplifies our calculations. We don't have to worry about bigger radiuses or smaller radiuses and how that messes things up. Radius of 1 is nice and simple. So in this case, here is our nice relationship between degrees and radians. 360 degrees, the full rotation, is equivalent to 2 pi radians. We're going to use that to help us convert between these two things. Here's a little animation of what I was talking about. So here's a radius, creates a circle, r. If we take that radius and we make an arc length of that amount, we can watch how it kind of goes around the circle. So that's 1 radian right in there. That angle is 1 radian. And we'll make 2 radians, see what that looks like. 2 radians. 3 radians. If we pause it right there, you can see that little bit more is pi, 3.14. And then a full rotation being 2 pi. So radians technically are a unitless measurement. Because of the way it actually gets calculated, we actually eliminate units here. Because what we're doing when we actually figure out radians is it's a ratio of the arc length s divided by the radius. Both of those have some sort of a unit. So it's s unit divided by r units. And when we divide these, those units actually cancel out. So we're left with something that's technically a unitless measurement. It's a ratio of the arc. That's really useful. That's something that really gives us a lot of power to using radians to solve for some things that make our formulas a lot simpler. For us, all we really need to know is that radians don't technically have a unit. Even though we might say an angle is some number of radians, that radian isn't really a unit. Unlike, you know, inches or feet or degrees or something, that's not, it has a certain definitive size, but it doesn't actually have a unit that's associated with it. All right, so let's do some conversions here. So we know, based on the previous slide that we had here, that 360 degrees is the same thing as 2 pi radians. 2 pi. So what would 180 degrees be? That's half a rotation, right? 180 degrees is halfway around a circle. So it's going to be half of this, half of the number of radians. So it's going to be pi. What about 90 degrees? Well, 90 degrees is a quarter rotation. If we take a quarter of 2 pi radians, 2 pi over 4, 2 over 4 is 1 over 2, so this is pi over 2 radians. That's not how you spell that. Let me erase that proper. And we can kind of keep doing this here, but 30 degrees, well, 30 out of 360 is 3 out of, that's 1/12 of a rotation. And 1/12 of this, well, 2 pi over 12, it's pi over 6. Pi over 6 radians. When we give radians, a lot of time our answer is going to have pi in it. If it doesn't, it's probably going to be kind of a funky angle. So a lot of times our answer, our angle measurement in radians will involve pi. If it doesn't, then we're going to have a decimal approximation. But for the most part, when we give an exact answer, we're going to be dealing with pi in some way. So let's just kind of do a little simple formula. So radians and degrees are proportional because they're measuring the same thing, and well, obviously 0 degrees is the same thing as 0 radians. So the proportionality can actually help us sort of create a formula that helps us kind of go between them. That way we can do kind of non-standard angles. We were doing some stuff that was pretty standard on the last slide. So if I solve this proportionality relationship, so the angle measurement in degrees divided by 360 is equal to the angle measurement in radians divided by 2 pi, because we know those two things are equal. I'm going to be able to get a formula here. So let me go ahead and solve for the angle measurement in degrees. So to do so, I would simply multiply by 360 on both sides, right? So my angle measurement in degrees is going to equal, well, 360 and 2 are both divisible by 2. So I can do that. I'm going to get the angle measurement in radians times 180 over pi. Now, I kind of separated that angle measurement out there in radians out of the top because that's something that we can do. We can factor it out of the numerator. So here's what we do. To find an angle measurement in degrees, we take our angle measurement in radians and multiply it by this constant. That's going to be the formula we use. Really similar to make this happen the other direction. To solve this same formula for angle measurement in radians, just going to kind of quickly do that. I need to multiply by 2 pi on both sides, so that gets rid of that. Well, 2 and that, those are both divisible by 2, so we end up with pi over 180 here, so we end up with pi over 180 times the angle measurement in degrees is going to equal the angle measurement in radians. So there we go. Similar idea. To find the angle measurement in radians, I take my degree measurement and multiply it by this, pi over 180. These are going to be two very useful formulas for us to convert back and forth. Again, it lets us convert really any measurement we want. So if we knew our degree measurement was 37 degrees, we don't have to figure out what fraction of a rotation that is and do kind of some weird convoluted, complicated calculation there. We can just kind of do this. It's pretty straightforward. You can think about it. There's any number of ways that people have created memory devices to help you remember this, but I just like to think about where the pi is. My angle measurement in radians is probably going to have pi in it, so I need to divide by pi to get the pi out of there because degrees don't usually have pi. If I want an angle measurement in radians, I need to give it pi. So I need to multiply pi in there to make it a measurement in radians. That's the way I like to think about it, but it's up to you. So here, real quick, just kind of a summary of those two formulas we just talked about. So if we want to figure out an angle measurement in radians, we multiply the degrees by pi over 180. If we want to go the other way, we multiply the angle measurement in radians by 180 over pi to give us degrees. Very simple process. Obviously, we want to make sure we do reduce it to simplest terms, especially when we're going into radians and we're probably dealing with a fraction in the end. All right, so let's go ahead and do a few examples here. Again, take your time and pause it if you want to try these on your own. So these are degrees, so I need to give it pi, so I'm going to multiply by pi over 180. 135 and 180 are both divisible by 45. Now that might not be so obvious. You might have to do some shorter steps in that, but they're both divisible by 45. This one goes in there 3 times, and this one goes in there 8 times. So by doing that, I end up with a measurement of 3 pi over 8 in radians. 300 degrees, so same idea. We need to give it pi, so we're going to multiply by pi over 180. These are both divisible by, well, easy, cancel out the zeros. That's something you can do sometimes, is if they both end in a 0. So 30 and 18, those are both divisible by 6. So 30 divided by 6 is 5, and 18 divided by 6 is 3. So 5 pi over 3. When you're doing these, especially when you're doing the delta math assignment about this, take the time to do it by hand. Don't just like use some sort of online calculator thing. You really need to understand this. So if you're not doing the assignment to really understand it, you're not doing it worthwhile, okay? All right, now we're gonna go the other way. We're gonna go from radians to degrees. So we're gonna be taking the pi away. So we're gonna be multiplying by 180 over pi. Okay, so that cancels the pi's out. That's what I mean by taking the pi away. And then we got to do a little multiplication here, but first, before you multiply, it's useful to simplify. So 180 and 6, they're both divisible by 6. This is 30 over 3, 1, obviously. 6 divided by 6 is 1. And then this ends up just being negative 5 times 30, which is negative 150 degrees. We're dealing with degrees now, because this does technically have a unit of degrees in it, right? And then here, 7 pi over 4. Again, we're going to be dividing by pi, so we're multiplying by 180 over pi. The pi's go away. And then 180 and 4 are both divisible by 4. It's going to be 45 and 1. And then 7 times 45. Ooh, that's a tough one. That's 90, 180, 270, 315. Yeah, 315. It doesn't hurt to have a calculator on hand, but definitely try to do this by hand. You'll get better at it. You'll also remember some pretty standard angles that come up quite a bit. All right. So last way, we've already kind of delved into the sum, but another way that we can measure angles is how much, what fraction of a full rotation, or how many full rotations, or how many and what fraction of rotation takes place. Not too difficult here, but we know that one rotation is equal to 360 degrees. So 1/3 of a rotation, we'll abbreviate that rot. Well, if we want to convert it to degrees, we could do a little stoichiometry here. So we can do 360 degrees over 1 rotation. This is an equivalent, this fraction here is equivalent to 1, because these quantities are equal to each other. 360 degrees is equal to 1 rotation. So essentially what I'm doing here is I'm multiplying 1/3 times 360. The rotations are canceling, and we're left with the unit that we want of degrees, right? So 1/3 times 360 is 120 degrees. How many radians? We're going to radians here, is in 2 1/4 rotations. So I'm going to give that to be a mixed number here. So 2 1/4 is 9/4 of a rotation. And I'm converting this to radians. So 2 pi radians is equivalent to 1 rotation. So this is a fraction that is equivalent to 1. So when I multiply it, I'm not changing the value of it, I'm just converting, because our rotations are canceling, 1 in the numerator, 1 in the denominator here. And now I can just kind of do this calculation here. 9/4 times 2 pi, be 4, and the 2 cancel a little bit. Those can simplify. They're both divisible by 2. So in here, when I do this calculation, I'm in 9 pi over 2. And again, this is in radians now, because the unit radians aren't really united, but the measurement we're dealing with now is radians. Last one here, 20 pi over 3 radians. So 20 pi over 3, this is in radians. We want to convert this into rotations. So 1 rotation is equivalent to 2 pi radians. Radians, even though they're not really a unit, the idea of radians are canceling out here. And I'm ending up with rotations. The pi's cancel. 20 and 2 are both divisible by 2. So we get 10, 1 here. So now we have 10 times 1 over 3. So this is 10/3, 10 over 3 rotations. We could change that to a mixed number if we want, 3 1/3 rotation. I think I called this a mixed number before. That's an improper fraction. Head bigger than the body, right? Head bigger than the... Anyway, that is our answer there. Again, doing these problems, making these conversions, dealing with the fractions, we're going to want exact answers when we're doing this. So don't give decimals. Work with the fractions. All right, so this is kind of a picture that you're probably going to become familiar with a little bit. Has a lot of really standard angles that we're going to use a lot on there. They're all multiples of 30, 45, 60, 90, something like that. And we use them a lot, okay? So knowing these particular angle measurements in degrees and knowing their approximate location is going to be useful. It's something that you're going to, even if you don't sit down and memorize it, it's something you're going to internalize a little bit. Same thing for radians. So right here is a nice chart, perhaps to even kind of start to memorize a little bit of. We have some common angles both in degrees and radians in here. Same angles that we just had on that previous one, but we're also including degrees in there. The thing I will point out is that the different colors do actually mean something. The blue angles are going to have similar properties, and the red angles are going to have similar properties, and the green ones as well. They come up a lot. It's useful to have some of them memorized to have really good understanding of them. Next idea here, coterminal angles. So coterminal angles are really just angles that, when we draw them in standard position, they look the same. They have a terminal side that actually lines up in the same place. Now, we may not get there in the same way. One of them might be a positive rotation, one might be a negative rotation, or one might be multiple rotations, but just ending up in the same spot. A lot of different ways we can end up with coterminal angles, but it is nice to know whether they exist. Because generally, we're always going to want angles when we're dealing with trig. We're going to try to simplify it and figure out our angles are going to always be in between 0 and 360. So including 0. In between 0 and 360. Or if we're dealing with radians, in between 0 and 2 pi, right? Even if our angle is multiple rotations and it's a much bigger angle than 360, we're going to figure out which angle is coterminal, which has the same ending spot, and work with that angle instead. It's an important idea, something we're going to do, but yeah. All right, so here we can see we have a 140-degree angle. Initial side, terminal side, is coterminal with a negative 220-degree rotation. Same position, two different angles. They are going to have the same properties associated with them. Really important idea. Again, those aren't the only type. So here we have a couple coterminal angles. 80 degrees and 800 degrees are coterminal. They end in the same spot because 80 degrees is just 80 degrees counterclockwise, right? This one here is 800 degrees, multiple rotations. It's actually 2 full rotations and then an extra 80 degrees, right? And you can see that here. Well, 800 is really just 80 degrees, which is the coterminal angle, plus 2 full rotations. Now, technically, there are an infinite number of coterminal angles for any angle that is between 0 and 360. I could come up with one right now. So let's say we're thinking about another angle that's coterminal. Well, what about 80 plus just 1 rotation, so plus 360, right? That would give me a 440-degree angle, coterminal. I could do 80 plus 3 rotations, which is 1,080 degrees. So that would be 1160, coterminal. It's going to end in the same spot. So, and you could imagine how this gets infinite, right? I could add any number of rotations I want. I could even add negative rotations if I wanted to it. I would always end up in the same spot. Because if I'm here and I add a full rotation, I end up in the same spot. Doesn't matter which way I go, positive or negative. That was supposed to be one for you to guess. What is coterminal with 315? Well, 45. It's supposed to, yeah, whatever, it doesn't matter. Negative 45 is 1. Let's come up with another one. What's another one? Let's add a rotation to it. So 315 plus a rotation, so plus 360 would be 675. That would be another coterminal angle here. It would end in the same spot. Silly me. All right, so this one here is what angle is coterminal with 19 pi over 4? That's radians, so that a little bit trickier here. Same idea though. I mean, we can add or subtract full rotations, but in this case, full rotations in a radian measure is 2 pi. So 19 pi over 4. If we take away 2 pi, 2 pi is really 8 pi over 4, right? If I take away that gives me 11 pi over 4. So that's one coterminal angle, but actually I can take away a whole nother rotation from that. Because 11 pi over 4 is actually technically still more than 1 rotation. It's more than 2 pi. So if I take away another full rotation, another 8 pi over 4, that gives us 11 minus 8 is 3 pi over 4. So both of those are going to be coterminal with that. Well, in fact, I could even go further. I could figure out an equivalent negative angle if I wanted as well, right? I mean, Not any particular reason to necessarily do this, but I can take away another rotation, another 8 pi over 4, which is, remember, the same thing as 2 pi. That becomes negative 5 pi over 4. All of these angles are coterminal. They're going to end up in the same spot. The terminal side here is going to be the same. It's going to be in the same location, and we always put our initial side in the same spot. That's what makes them coterminal. All right. Last thing to do today are reference angles. So reference angles are always between 0 and 90. They're an angle that's between 0 and 90 degrees. Or if we're doing it in radians, it's going to be between 0 and pi over 2. That's the equivalent of 90 degrees in radians. So they're always going to be between those two. And every angle has a reference angle. What you do to find the reference angle is it changes a little bit depending on what quadrant we're in. So in this case, we're in quadrant 1. We take our terminal side and we measure the angle, the shortest distance between the terminal side and the x-axis. So in that case, it's right here. It's the same as the angle. It's a 60-degree angle. The reference angle is 60. The important thing with reference angles is that every angle that has the same reference angle has very similar properties. So we can use reference angles to greatly simplify our problem solving. Even if we're dealing with a 315-degree angle, we can simplify that to only dealing with a 45. It lets us memorize less stuff, understand less stuff, but apply many more properties. Anyway, let's talk about it again. So here's a 120-degree angle. Here's our terminal side right here. The shortest way to get to that x-axis, again, remember x-axis down here, is to measure it this way. So this is a 60-degree angle. So our reference angle, sometimes we write this as theta ref, is 60 degrees. The reference angle for a 120-degree angle is a 60-degree angle. It has the same properties as a 60-degree angle, and we make use of that. Same idea here. Here's a 240-degree angle. The shortest way to get to the x-axis is to go right there. Don't go all the way this way because that's greater than 90. That's a longer way here. So again, a 240-degree angle has a reference angle, a theta ref, of 60 also. And here, a 315-degree angle, the shortest way to get to the x-axis is right there, 45 degrees. In this case, our reference angle is 45. That's how we do reference angles. We find our terminal side, and we find the shortest path to get to that x-axis, and that measurement there is our reference angle. All right, we're going to go ahead and stop that right there. And yeah, lot to digest. See you guys later.